All right, this is lecture number 3 of Agricultural and Biosystems Structures Engineering. The topic is on estimating agricultural loads. And before proceeding with that, the topic will be on the design process, okay, of structures and buildings in agricultural and biosystems engineering. Now, as you can see, okay, the whole process of designing, okay, from or in development of structures and buildings from the planning stage up to the end of life of the structure during the commissioning, okay, it involves a lot of engineering work from front-end engineering to the construction and development to the commissioning. Okay. Now, in the course of AB structures engineering, while this will be focused on the front end, okay, because it is a requirement of the course for the student to create or to make or to develop a building plan, okay, 7-sheet building plan that comprises particularly the planning and design phase. Well, in consideration of the lifespan of a building, okay, that includes life cycle analysis. Okay, usually a building lasts 50 years, and after which it should be assessed of its possible service life. Okay, and in this process, okay, what is the very important portion of this is the structural analysis and design, because without this, okay, the structures would not be there in the first place. And it's important that the structures are able to resist the applied loads without failure. And if failure is due, okay, the proper corrections during the service life. Okay. Okay, let's proceed with the estimation of structural loads. And when we're talking about the structural loads, okay, during the planning phase, it is important that the necessary requirements and factors should be identified early on. Okay, the layout, the dimensions and specifications. It's important to select from among a variety of alternatives to solve, okay, the demand problem. Okay, well, no, not really exactly demand problem, the demand considerations. Okay, and the considerations usually in engineering structures and buildings are the following. Okay, you have the structural considerations, the constructional considerations, and there's also the function and non-functional considerations. When we say non-functional, this could be broken down into aesthetics, sociology, law, okay, everything related to the legal aspects of the construction. There's also economics and environment. Okay. When you say structural, okay, one would refer to the nitty-gritty of the computations that would enable the support the functional aspect of that the structure or building. Oftentimes, the structural would extend towards the non-functional, like in an actual architectural considerations. Okay, often would be leading to functional and non-functional. The construction also be able to support those architectural requirements. Okay, be it aesthetics. Okay, and that's the various functioning portions of a building design. Okay, you have your architectural as well, which falls under functional and non-functional. So in the structural sense, okay, because this is a structural engineering course or structures engineering course. The focus will be merely on the structural aspect, and that's why we have to talk about loads, because the building, okay, in essence, functionally should be able to support the loads that the building or structure is meant to support. And in essence, okay, there are two loads considered in structural engineering: the dead loads and the live loads. Later, we'll discuss further what live loads are referring to, but here we focus on the dead loads. And the dead loads refer to the mass of the building elements, okay, that's supporting the whole building itself. So you have there the footings, the foundations, the walls, the suspended floors, the frame, the beams, and the roof. And generally, okay, these are simply the weights of all the structural members and materials that are permanently attached to the structure. Now, since these are fixed and then permanently attached, these are easier to determine or compute for. And this could be easily derived based on assumptions. Okay, like for example, in uniformly distributed wooden beams, okay, for a 10 feet span, okay, that would be 2% of the total load. And for a 20 feet span, okay, that would be 10% of the total load. That's the dead the dead load. Okay. Again, for dead load, the dead load of wooden roof trusses, okay, we have here a formula that can be used. W is the weight of one truss, and you have the S is the bay or distance between adjacent trusses, okay, in feet, and you have the span of the truss in also in feet. This could be applied, for example, in the wooden roof truss of a chicken layer building shown, okay, and you have the dead loads in the roofs, the beams, and the posts. And this equation can be used for the wooden roof trusses as shown in the image. Now, the weights of materials in constructions, these are very important and usually assumed, okay? And you have your table number 1 showing the mass of the building materials. This is taken from the book of FAO, later shown in the reference. This is a Creative Commons book, so everyone can access this book. Let me know if you want to get access. Okay, so you have here for concrete, okay, you have your density, okay, that is 2,400 kilograms per m cube, and the steel is 7,800 kilogram per m cube. Dense wood, okay, for softwood, you have your plywood, okay, kilogram per m squared. Galvanized iron sheet for roofing, and your concrete hollow block, depending on the size, okay, and the brick wall, okay. These are in kilograms per m squared. Now, for dead loads, you could also include the weight of the fixed service equipment. What are examples for this? You have your boiler, for example, okay, or your air conditioning unit, which are fixed to the structure or a building. Next, you also have your vegetative and landscaping in your building. You have also your solar panels, which are also fixed atop the topmost floor, okay, or the roof. Now there are, okay, specific or specified weights for these materials, and this could be determined easily by merely arithmetic. So quantity times the weight, so you get the total weight based on example the density of the material. All right, so you have here now the live loads, and this is the variable load atop or within a structure, and this includes usually gravity loads that are temporarily applied to the structure. In the computations, this should be considered, okay? So that's why well, usually this would include your biological loads, the mass of the animals, the people, and also the mass of the movable equipment, or the um, mobile, okay, the mobile equipment, and materials such as food and feed, and also your consumable materials. An example for this, okay, continuing from the image a while ago, you have your chickens as a live load inside this chicken layer building, and also the personnel, and also um, the appliances, or the equipment inside the structure. Okay? You're feeding your feeders. Okay, that is also a live load, plus the feeds. Okay, the feeds that are uh, fed to the chickens or the layers. There are other live loads that to be considered in structures, and one of which would be your wind load. This is assumed, okay, based on the conditions of the area. You have here the equation Q equals to 0.0127 V squared times K. This is an empirical equation based on observations. So that's a difference between your equations and derived equations to your empirical. So you have your Q, the basic velocity pressure in Pascal. Okay. Later we'll see the demonstration for this one. You have your V, your wind velocity in meters per second, and your K, okay, factor, which is the equation, the quantity H over 6.1 raised to the fraction 2 over 7. H in K is the design building height of the building. And this is usually the eve height for low and medium roof pitches in meters. Okay. Now the 6.1, okay, is the height where wind velocities have been recorded, and this is table number 2. Again, this is from the FAO. Okay, table number 2. Okay, differentiates the wind the wind, and classifies them into strong breeze, okay, strong breeze, moderate gale, fresh gale, okay, strong gale, hull gale, and then the storm, okay. And based on the description, one can determine the velocity at height, the velocity at height. So the V, okay, would depend, okay. Now, the H, okay, would depend on the height of the building, because you have your velocity at height, and then you have a factor K to determine the factor to the velocity. Okay. Now for strong breeze, you have the large branches in motion, whistling and telephone wire, umbrellas used with difficulty. Now it goes stronger as it goes down the scale. This scale is called the Beaufort wind scale. Okay, it also used in wind resource assessment. Okay, the storm, you have already widespread destruction, and the velocity at the specified height is 33 meters per second. Okay, so one will just have to determine the description of the wind, and then determine the wind classification, and then get the velocity over here on the for the specified height of 6.1 meters. Live loads on the wind is also dependent on the side where there is this action of the wind. Okay, you have your leeward and windward side. Okay, the windward and the leeward. Okay, the leeward and the windward side. Now the wind would be acting on, for example, from this direction. So it's when it's the windward, it's where the wind is acting on. Okay, so you have your P, design wind pressure, equals to the C. Okay, the C asterisk, okay, height CH, exposure CE, and gust factor CG coefficients. Okay, these are the coefficients and are unitless. So the CQ is the pressure coefficient. QS is the wind stagnation pressure, PA, okay, which is also derived or determined using the 1/2 rho V squared. That's a familiar equation, I think. Okay, that's a QS. That's pressure. Okay, and the I is the importance factor, and it's unitless. Now, how do we get for these values? Okay, you have here the values for the various coefficients. Okay, your wind pressure coefficient CQ for gable. Now, this is for gable roof type farm buildings, and you have your windward roof coefficient for roof slope, and you just have to determine that slope. Okay, in between you could interpolate. And then you have your completely closed gable roof type. Okay, and then you have your different um, um, ratios for your gable roof type depending on your design. And okay, this is the final value, okay, for your CQ. Okay, for leeward roof portion, you have this load. Okay, so you have now your CQ, and you have your other C prime, C sharp, C asterisk. That has to be determined. For the importance classes, you have depending on the windward roof coefficient, roof slope, and the importance factor is easily determined using this factors based on your category of your building. And the windward roof coefficient is dependent on the type of the building, okay, and the risk that it has for human life. Okay, if it's hazardous, okay, or high occupancy, that is a public or private building, you have to consider a higher importance factor. This is similar to the safety factor introduced in machine design. Okay, if one is familiar with that design process. For essential facilities such as hospitals, fire and police stations, and designated urban shelters, where there is the requirement for higher load capacity, okay, you have to multiply that by a factor of 1.15. And this is lower for at 0.77 or 0.87 for structures and buildings that there's low risk for human life. Okay, and this is not limited just simply to rural storage or temporary facilities. But for more normal occupancy, you just have a multiplier of 1.0. Okay, housing, farmhouse, offices. Okay, for commercial establishments. Okay, now, okay, the loads on suspended floors. Okay, you have the load of the animals or equipment. Okay, this is dependent on the machinery. One has to look into the specifications of an equipment to determine the weight. And for the animals, okay, these are identified using this known loads or assumed loads for tie stalls, for loose housing, for young stock. That's 180 kilograms. These are for cattle, and then you have also for sheep, for horses, for pigs, for poultry. Okay, deep litter, and you have your cages. Slatted floor for pigs that are 180 kilograms. Okay. Slatted floor for 90 kilograms. There are a lot of references out there, so one can even look in other references, but this is based on the FAO 2011 book reference. And then you have your mass of farm products. Okay, different products have different weights and different angles of repose depending on the activity. For emptying, okay, for filling, you have also your mass, okay, of the material. For rice that is in paddy form, it's 577 kilograms per m3. Maize, okay, that's shelled, maize with ear, okay, the wheat, soybeans, dry beans, potatoes, silage, groundnuts, and hay. It's important to determine the material properties, okay, and use this in computations involving structural loads. Again, this is the reference, load structures in the tropics, and I'll see you in the next lecture where we talk about beams.